Hello, I'm Wafer Agent. Today, I've prepared something a little special. I've spent years in the wafer industry myself, but I've rarely come across a resource that covers semiconductor equipment from wafer manufacturing all the way through final packaging in one place. So this time, I decided to put it together myself, because I was curious too. Semiconductors are made through thousands of process steps, but what drives those processes is ultimately the equipment. In this video, we'll walk through the key equipment used at every stage: wafer manufacturing, front-end processing, inspection, packaging, and final testing. After watching this one video, you'll have a clear picture of what equipment does what inside a semiconductor fab. Here's the full flow, starting from silicon, crystal growth, wafer manufacturing, front-end process, inspection, packaging, and final test. Let's go through each stage and see which equipment matters most.
First up is the CZ grower. The CZ grower uses the Czochralski method to grow silicon single crystal ingots. High-purity silicon feedstock is melted at extreme temperatures, and a seed crystal is slowly pulled upward while rotating, forming the ingot. This ingot is the starting point of every wafer. To produce a 300 millimeter wafer, you need an ingot with a diameter of at least 300 millimeters. Keeping impurity levels and crystal defects extremely low throughout this process is absolutely critical. Key makers include PVA Tepla from Germany and Ferrotech from Japan. In addition to the CZ method, the FC, float zone method, is used for high resistivity specialty wafers.
Next is the wafer slicer. This equipment cuts the grown ingot into thin wafers. The most common approach is the multi-wire saw, which uses diamond wire or slurry wire to slice hundreds of wafers simultaneously. For 300 millimeter wafers, the target thickness is approximately 775 micrometers, and slicing precision directly affects wafer quality. Key makers include Meyer Burger from Switzerland and Takatori from Japan. After slicing, the process continues with edge grinding, lapping, and polishing.
Third is the wafer polisher. Because sliced wafers have rough surfaces, they need to be polished down to a mirror finish at the nanometer level. The process starts with lapping for coarse material removal, followed by polishing to achieve the final mirror surface. This is where critical wafer specs are determined, flatness parameters like nanotopology and SFQR. Since lithography precision in front-end processing depends heavily on wafer surface flatness, the polisher plays an essential role. Key makers include Okamoto and Speedfam, both from Japan. Fourth is wafer cleaning equipment. As the final step in wafer manufacturing, it completely removes particles and metallic contamination from the wafer surface. RCA cleaning applies SC1, SC2, and HF solutions in sequence to progressively remove organics, metals, and oxide layers. Scrubber systems add physical cleaning using brush contact. Wafer cleaning isn't just performed before shipment, it's repeated between each step throughout the entire front-end process. Key makers include Tokyo Electron and Screen Holdings from Japan, along with Lam Research and Applied Materials. Now let's move into front-end process equipment. First is the oxidation furnace. This equipment forms a silicon dioxide, SiO2, oxide layer on the wafer surface, operating at high temperatures between 800 and 1200 degrees Celsius. It's used to form gate oxide and field oxide layers, and also for impurity diffusion and annealing heat treatment. Operating in batch mode, it can process dozens to hundreds of wafers at once, making it highly productive. Key makers include Tokyo Electron, the global #1, along with Kokusai Electric and ASM International. One of the most critical pieces of equipment in front-end processing, the EUV lithography scanner. This machine, supplied exclusively by ASML, uses extreme ultraviolet light at a wavelength of 13.5 nanometers to expose circuit patterns onto wafers. It enables patterning below 2 nanometers, making it the defining equipment of modern semiconductor miniaturization. A single EUV system costs approximately $200 million,
and semiconductor fabs worldwide depend entirely on ASML to supply them. Canon and Nikon, with their RF immersion scanners, continue to play important roles as well.
This is the etch equipment, responsible for the etching process in front-end manufacturing. Based on the photoresist pattern, it selectively removes unwanted films. This is the core step that defines the shape of semiconductor circuits. Dry etch uses plasma for precise material removal and is especially critical for high aspect ratio hole etching in 3D NAND. Wet etch uses chemical solutions for isotropic etching as a complementary approach. Key makers include Lam Research, the global #1 in etch, Applied Materials, and Tokyo Electron. Next are CVD and ALD deposition equipment, which handle thin film deposition in front-end processing. CVD forms films on the wafer through chemical reactions, while ALD enables atomic layer precision deposition, one layer at a time. These tools deposit a wide range of films, dielectrics, metals, polysilicon, and are used throughout the front-end process, from gate dielectrics to intermetal dielectrics. As transistors continue to shrink, ALD becomes increasingly indispensable. Key makers include Applied Materials and Lam Research from the US, and ASM International from the Netherlands, a specialist in ALD. This is the ion implanter, which handles the ion implantation process in front-end manufacturing. It implants dopant ions into silicon to give it P-type or N-type semiconductor characteristics. By precisely controlling ion energy and dose, it forms the transistor source, drain, well, and threshold voltage regions. Ion implantation directly determines the electrical characteristics of semiconductor devices, making it one of the most critical process steps. Key makers include Applied Materials with its Varian ion implanters, Axcelis Technologies with the Purion series, and Sumitomo Heavy Industries from Japan. The last key equipment in front-end processing? CMP, Chemical Mechanical Planarization. Using slurry and a polishing pad, it planarizes the wafer surface and removes topography between layers in multi-level wiring processes. It's applied across a range of steps: STI planarization, tungsten plug fill, and copper interconnect polishing. As semiconductor scaling continues, managing interlayer topography becomes increasingly demanding, and the role of CMP grows with it. Key makers include Applied Materials with the Reflection series, Ibara Corporation from Japan, and KC Tech from Korea, a domestic CMP leader. After front-end processing, every wafer must go through inspection. The wafer inspection system detects surface defects, measures circuit line widths, and verifies interlayer alignment accuracy. Combining optical and electron beam inspection, it identifies particles, scratches, and pattern defects, enabling early detection of process anomalies and effective yield management. In the AI era, the role of inspection equipment is more critical than ever. A single defect can translate into losses of hundreds of millions of dollars. Key makers include KLA Corporation, the global #1 in inspection, Hitachi High-Tech for e-beam inspection, and Onto Innovation for overlay and CD metrology. Now let's move into packaging. First is the wafer dicing saw. This equipment cuts the completed front-end wafer into individual dies. There are three main approaches: blade dicing, laser dicing, and stealth dicing, where an internal laser processes the wafer from within. As wafers become thinner, the precision demands on dicing technology continue to rise. Key makers include Disco Corporation from Japan, the global #1 in dicing, and Tokyo Seimitsu. The second key piece of packaging equipment, the wire bonder. After the diced chip is attached to a lead frame or substrate, gold or copper wire is used to create the electrical connection between the chip and the package. The two main methods are ball bonding and wedge bonding, both using a combination of ultrasonic energy, heat, and pressure to form the bond. Wire bonding is applied across a wide range of package types: lead frame packages, BGA, QFP, and more. Key makers include ASMPT, the global #1 in wire bonders, Kulicke & Soffa from the US,
and Shinkawa from Japan.
Finally, we reach the final test process. The test handler automatically loads and unloads semiconductor packages into and out of the tester. It performs testing under both high and low temperature conditions, automatically sorts defective units, and organizes parts into trays. It's applied across all semiconductor categories: memory, SoC, power semiconductors, and more. Key makers include Advantest from Japan, the global #1 in test handlers, along with Teradyne from the US, which offers integrated handler and ATE solutions, and Kohu. The core equipment of final test, ATE, Automatic Test Equipment. It automatically measures and inspects the electrical characteristics of semiconductors, running functional tests, speed tests, and leakage current measurements. It's used at both the wafer level, EWS, or electrical wafer sort, and for final outgoing inspection after packaging. Key makers include Teradyne from the US, the global #1 in ATE with the UltraFlex platform, and Advantest from Japan, known for the V93000 series. As we've seen in this video, semiconductors aren't made from wafers alone. Equipment for growing wafers, patterning circuits, inspecting defects, packaging dies, and testing finished devices. All of it works together to complete a single semiconductor. Understand the equipment, and you understand the entire semiconductor industry. This has been Wafer Agent.